So this is where we are currently at with our simulation. And like I mentioned earlier, the movement is pretty much set. And all we have to do now is really add our colors. And we'll do a lot of adjustment in terms of color, but especially P-scale, because we really want a specific look for this effect. Now, in order to create our color, what I would like to do is create a gradient across our grid that goes along sort of like our width. So it goes from here to here. And in order to create this type of coloring, we can go back to our line over here at our match size, and we can add a rest attribute for our line as it is. So if we add our rest over here, this will be carried over when we do our copy to points, and it will be carried forward in our simulation. So if I reset the simulation, let's go ahead and from here we'll do an attribute VOP. We'll rename this one set CD, color this orange. So let's grab this, color this orange. And if we step inside, we can go ahead and let's bring in with a bind. We'll bring in our rest, set this to a 3 floats. And for our rest, we are really interested, if we look at this, we are just interested in the Y component. So if we go back here, we can do a vector to float. And since our line, if we go one more time back up, since our line is in the middle here, if I do spacebar 4 to go in the right view here, we can see that our Y dimension goes from negative 0.5 to around 0.5. So this is how we have to remap our values. So if I go back into the set CD attribute and in the perspective view, here we'll grab our Y component, so the second value here. Let's do a fit range, and like I mentioned, we will want the source mean to be negative 0.5 and our source max will be positive 0.5. So hopefully now as I plug this into the CD, we will get this gradient exactly how I mentioned that we want this. So we have this nice gradient now from white to black across the width of our slices. So now we can further control this. Let's go ahead and first of all, we will also want to do a ramp, and let's actually use some colors here. So this will be ramp CD. We'll also do a label here, and if we go up, we will set our white point here to be a blue color, and we want to desaturate this, and we might want to increase the color even more. We'll start off with something like this. We'll transfer this over to rendering. So this will be important, the color that you set over here. So let's go back inside and we can further control this ramp. If let's make some room here. And first of all, let's drop down another ramp, and this will be our ramp. Let's do width, and let's also paste this in the label, set this to a spline ramp, and I will plug this before our color ramp. And now if I go up, let's go ahead and reset our ramp width here, and we can maybe do an exponential ramp. We can sort of skew this a little bit more towards the bright spots. So let's set this to a B-spline, and we'll do something like this. Maybe we can go back inside and we can play around with the fit ranges values over here. I can maybe set the source mean to an even lower value, just so I can increase this spread of the gradient. So this is good for our base, but I would like a little bit more emphasis on this bright spot over here. So I will drop down another ramp, and let's rename this one to ramp. Let's do something like underscore bright. We'll paste this in the label as well, and we'll also set this to a spline ramp. So we will just add this on top of our original ramp over here. Let's drop down an add. And so this is our ramp width, and we can use a different fit range over here. So let's duplicate this one. This will also point to the same value. Let's plug this in our ramp bright, and if I add this on top, we kind of have the same result. But now as I start to increase the source mean, let's maybe check. We will have to reset our ramp bright over here. So let's control middle mouse click to reset this ramp, and we can also squeeze this even further with this exponential ramp and skew this towards the bright spot here. So we essentially just grabbed the same kind of ramp that we had earlier, but we just added another extra one on top. So if I go back inside and if I were to disable this add node, we can see how most of this brightness that we are adding with this second ramp will be focused around this area here, and maybe we can even spawn a little bit more points. Let's go to our scatter and let's try a value of 300 here and reset our simulation just so we have more points so we can clearly see what we are doing. And maybe also I'll press D and set the background here to dark. All right, so here we have the current effect as it is, and we might want to go to our ramp here, and I want this bright part over here to be even brighter. We can go ahead and make some room for another key over here, and maybe this one I can skew more towards white. We'll do something like this. And again, to preview the frames better in our viewport, we can go ahead and drop down an attribute wrangle, and this will be our viewport prev. And here we'll say that at CD we want to multiply this, so we'll do multiplies equals a ch. Let's do ch or rather cd mult in between parentheses. So we'll just create a new channel, cd mult, and we also want to modify our alpha. So here we'll do also at alpha multiplies equals ch, and we can do alpha mult or something like this. All right, so we can add these parameters, and let's increase the alpha and increase the color. So we'll do the CD mult here. Let's multiply this by 25. And the alpha, let's leave this as it is for now. But now, hopefully, we can kind of see when our colors accumulate. And this is how we will actually render them with the emissive channel. We have a much better idea on how this effect will look. So if I go back to the set color here, I can maybe skew this bright part. We can see now, especially if I were to go inside and if I were to disable this add operation, how this changes our look with this bright part over here. Now, probably this is a little bit too bright. We can still control this with our ramp over here. We might want to, let's maybe just get rid of this point and just use one key instead. And I'll maybe just want to pump a little bit more white into this, so just desaturate the value. All right, something like this will be fine. We can come back later as we are doing some test renders as well. But this is essentially how we can set the color, and the color is set more or less, but what's more importantly here will be the p-scale. So I want to do quite a few adjustments for the p-scale. So for our p-scale, let's go ahead and start off with an attribute vob first of all. So we'll create one and we'll color this orange. Let's rename this one to set p-scale. And the first thing, we want to base our p-scale on the normalized age, so the n-age attribute. So we want the p-scale to diminish over time as our particles age. So we can go inside, we'll do a bind, and we'll grab our n-age attribute. Let's use a ramp here as well. So this will be our ramp underscore n-age. Copy this into the label, set this to spline ramp, and let's do a bind export to our p-scale. We'll do something like this. Now for our p-scale, obviously we will need to scale this down by quite a lot. We will need a global multiplier. So let's do a multiply here, and we'll promote the second input to a, let's use global p-scale as label, and we'll go up. Let's reset the ramp NH first of all, and we'll set the global p-scale here to 0.01. And like the other projects, we will further control this particle scale directly in Solaris, but this will be a good starting point for us. Now to preview the p-scale better in the viewport over here, let's go back inside, and before this multiply and export, I will want to preview the result of this ramp through the alpha. So if we do here a bind export and export this to the alpha, we can see that this will now give us some feedback in our viewport in terms of what the p-scale is doing. So we can better estimate how this will look in our render. Now, as I play the simulation further, we can kind of see our particles start to dissipate over time. Now, currently they are appearing over time, so we want the reverse effect of this. We can go up and we can reverse our ramp. So now as they spawn, they will have a full value for the p-scale, and as they start to age, they will start to slowly disappear, so get smaller and smaller, and we are seeing this again through the alpha in the viewport. Now in terms of this NH ramp, we might want to add one more point over here, and let's set this to a B-spline first of all, and I will want to have an exponential decay to them. I kind of want them when they first spawn to maintain their full p-scale for a bit, and then slowly start to taper off and then slowly disappear over time. Of course, you can experiment with the ramp values over here and find something that you like, but from my own experiments, this is the one that I ended up with. So another thing that we can do for our p-scale, we can also follow the same type of gradient that we have for our color. We can also introduce this for our p-scale. So we'll do the same thing that we did earlier. We can go inside our attribute VOP for the p-scale. We can grab our rest, or in fact, let's go up and let's go back in our set CD attribute VOP, and we can just grab the setup here with our rest, our vector to float, and our fit. Let's copy these and let's go up. Let's go inside the p-scale, and here we will want to do a multiply. Let's maybe make some more room. We'll do something like this, and let's add a multiply here after our ramp, and let's rewire the second multiply so it all points to the same multiply. And we will copy, let's paste the copies, the nodes that we had from our previous setup. So again, we have our rest. This is a 3 float. We are then splitting this with a vector to float, grabbing the middle value, and we have our fit ranges over here. So we can multiply this over our current NH ramp here. So when we do our multiplication, we can see this again through our alpha over here, how this is now affecting our p-scale. So we are now also scaling down our particles over this gradient generated from our rest. Again, I can enable and disable this so we can see this clearly. We can probably, let's enable this, and we can probably push down this fit range value here. Let's try a negative 7 for our source mean, just so we increase the spread a little bit, and this will be mostly fine. But now I would like to do something that's a little bit more complicated. I would like to scale down the particle scale across the length of each entire slice. So we currently have this scaling down, we have this gradient across the width, but we also want a gradient across the entire length. So to do this, we will need to reference our original curve geometry from where we get our leading points. So let's go up and let's look for our curves over here. We'll grab this, let's Control C, and let's duplicate one of our object merges, paste our path to the curves. All right, so we have our curve geometry. We want to reference this in our set p-scale attribute VOP. And now we can use the curve view value of our curve geometry over here. So if from here, let's run another resample, and let's place this in our chain, and let's enable the curve view attribute. So this is what we want. If I go to the information here and turn on the curve view attribute, we have this 0 to 1 value that's going across our curves, and we want to transfer this over to our particles over here. So we can use an XYZ distance. Let's step inside, and if we grab our op input 2, we'll do an XYZ dist. Let's point the position to our position. And for now, let's plug the primitive attribute inside the prim, and this will also need to point to our op input 2, and we'll also plug the prim UV into our UV slot. And we want to grab the curve view attribute. So here the attribute will be curve view, and this is a float attribute. Now let's see what happens if we plug this. Let's preview this in the color for now. So we have this result, and if for example now I will drop down another ramp, and we can call this one ramp. Let's do curve view, and let's also point this here. Let's set this to a spline ramp, and let's plug this here, and then here we'll plug this into the CD. If we go up, we can create a ramp that looks something like this. So it's brightest in the center, and this is what I want to transfer over to our p-scale. Let's maybe further adjust this so it's maybe has a better spread here, and we'll set this to B-spline as well. So we can do something like this. And now our p-scale will be also scaled down by this value as well. So we have this nice smooth tapering between the start and end of each of our slices. So if I go back inside, we can just plug this result from our preview and our ramp. We can just plug this in our multiply, and now I can disconnect this connection with our color, and we can see, let's maybe make some room over here. And now we can see, if I were to disconnect this, how this new operation, this new multiply changes our particles. And also let's preview this from our viewport display so it's a little bit nicer. We can see one small problem here, however. If we look at our particles, and let's template our particles and preview this resample node here for our curves. Let's maybe turn off the visualizer. We can see, and let's maybe actually preview our CD instead. We can see, for example, at this part over here, that this is where our curve ends, but our particles, because of the velocity inheritance and inertia, we spill some of these particles over, and most of these slices will extend the length of the original curves. So we can see this clearly over here where our line ends, where our curve ends, and where our slice particles end. So we need to somehow extend our curve geometry so we have the most accurate transfer of our curve view attribute. And to do this, we can go back to our curve geometry here in with this object merge, and we can just select the endpoints of these curves. So if we do a group expression and we do the same thing that we did earlier, we'll set this to points. For the expression here, we can use first point of primitive. Now, unfortunately, this is grabbing the other point. We can see that for this curve, for example, we need to grab the end point, not the start point. So instead of this expression here, instead of equal 0, we will do equal, and here we'll type at num vtx minus 1. So this expression here will return the last point of our primitives. And we can also rename the group here to end. And if we do an attribute VOP and we only run it on this end group, we'll select the group here to end. We can just push this point along our normal. And if we remember, we computed the normal of our curves with the polyframe. So we can see that we have this normal attribute that points along our curve. So if we go inside, and let's actually rename this one to extend curve and also color this orange. So if we go inside, we'll grab the position as it is, and let's remember that this attribute VOP will only run on this single point. So if we do an add operation here and we just simply add the normal vector that we already have, we get the opposite direction of what we want. So all we need to do here is do a negate, and we can see now that our point is pushed further along the normal of this curve. So if I were to enable and disable this add, this is what we get. And of course, we would like to control how much we are pushing this point, so we can just do a multiply here and promote the second input here. Let's rename this one to, we can do something like mult. So if we go up, we can now increase this, so we can push this as further along as we need. And if we preview our set CD points over here, we can see exactly how much we should push this. So let's increase this, and we can increase this even further. So we can do something like this. And now our particles, or rather our curves, will match the complete extent of our particles as well. So if we go back to our set P scale, now we will have the most accurate transfer of the curve view attribute. So this is the result that we have, and everything seems to be working fine. We can preview a few frames, and in fact, I think we can preview another flipbook here. So let's go ahead and show all objects. So let's go ahead and right click, and we'll do the same frame range here. Let's hit start. Alright, so if we look at the results so far, I can say that this is looking pretty good. We have pretty much everything we need. Now, we will still need a few attributes and adjusting, but this will mainly concern the rendering part. So we will do those when we get to the Solaris module. So for now, we are in a very good spot. We will also render more particles, so we will increase the overall count. We can see that we are working with roughly 1 million. So we will need something closer to 10 million, I would say. So we will increase this for our final simulation. So let's go ahead and we can cache this out as it is. Let's drop down a file cache here. Let's set this to the $job variable, and this will be our slice PRT. we'll render this, or rather cache this, from 1200 to around, we can cache this up until 1400. We know that at around 1365, where our switch happens, this layer should be probably completely disappeared, but we can just give ourselves a bit of extra padding and just simulate up until frame 1400. And let's also clean up some of our attributes here. We can do an attribute delete. So we will want to keep our age, our life, let's also keep our ID and the ID or rig. We will also need our velocity, and we also need our rest. So if we delete non-selected and disable the file cache, we can see that all of our operations run as it should. So these are the attributes that we want to keep, and we can go ahead. Let's save to disk. And I will just cache this lower quality simulation for now while we are working on the other effects. And like I said, when we get to rendering, we'll up the particle count and recache the final simulation. But for now, we are done with this layer, so we can do a null from here, and let's do out slice PRT. And with the next lesson, we can create one more layer by using all of this geometry that we already have, and we'll see what this layer is about. So with our current setup, we can still create one more layer while we are inside this effects container, which is going to be the planes that we can use for displacement. And also we will actually need these planes to exist in order to use them as a cutting geometry when we slice up our enemies. So essentially what we want to create is the same thing that we have over here, where we have these particles for each slice, but we would like to create an actual grid geometry along these slices as well. Essentially what we need to create is this layer over here, where we just have the planes going in the same direction and orientation as our particles. So if I were to compare this with our particles, we can see that this is where we have our particles, and this is going to be a plane representation. So we just need to create actual grid geometry from our current setup. So we can start with roughly the same setup that we have for our particles. So we will grab all of these nodes with our copy to points. Let's copy these and let's paste them over here. And again, we just have our lines following our leading points. Now in this case, I would like to just draw a line using the leading points, and then we use the sweep method set to a ribbon type, which will create our grid. So first of all, we need to create these lines. So we really just need one point here. So really we can just use our leading points as they are. Let's set this to point display, and we don't really need our copy to points either. If we plug this inside a pop network, so let's drop down a pop network from here. I'll set the simulation start frame also to 1200. So if we just run the simulation, let's step inside and we'll need to set our pop source here. We need to set the emission type to all points, and we'll keep the birth life expectancy here to 100 because we want all of the particles that we spawn to last up until the last frame. So if we go up and reset our simulation, now our leading points will just leave points in their wake, but of course these are still affected by the velocity. So we can go back inside, and in the attributes tab I'll set this to 0. So now again, one more time, I will reset the simulation, and now we can see that as our leading points travel along their curves, it will just leave some points behind them, and now we can use these points to connect all of them by using our ID or rig attribute. So from here, if I drop down and add, and I go to the polygons and set this to be by group, we'll set the method here by attribute, and we want to use the ID underscore or rig attribute. And we can see now that we essentially just recreate our curve geometry, but now it is also animated by using our leading points. So this is what we want. And from here, if we throw down a sweep node, and if we go to the surface shape here, we'll use ribbon, we can see we end up with this, and we can just increase the width here. Let's use something like 4. And also if I press Shift W, we can see that we can increase the columns. Now really, after we do our add here, we should run a resample just so we have a consistent point count between all of the frames. So we preserve this length between each point of 0.1. And now this in turn will make our sweep have more consistent topology. So if I look at this, we might want to increase the columns here. I'm kind of looking for kind of even squares here, so maybe we can increase the columns even more to somewhere around 40 or so. We don't really need to be super specific. But now this is the result that we have, so we can see that all of our grids that we are spawning here, this will follow exactly our slice particles. And we have a slight thing happening over here. We can see that when our particles first spawn, because it doesn't really have the next following particles to connect, we just end up with a set of points. So it's worth just throwing down a clean node, which will get rid of any of the unused points, as we see over here. All right, so now we end up with something like this. And if I template this with E and look at my particle simulation from over here, we should see, and let's set this back to pixels. We see that, let's maybe go back in time and go back to an earlier frame. Let's just focus where we just have one. Our planes should really be oriented with our slice particles. So if I go to the sweep node over here, we can go to the roll tab and we can just turn this. Probably we need to use 90 degrees, and now we can see we have the exact same orientation as our sliced particles. So now our planes are matching our sliced particles, and if we just look at this geometry through our camera especially, we have something like this. So this is what we will use to turn into this layer right here. We'll just create some attributes in which we can set the opacity for each grid individually. We'll look at this more in the Solaris section, but this is essentially the geometry that we need. Now we also need this, all of these grids to actually slice up our enemy geometry. So if I were to template this one more time and look at my remeshed geometry over here, we should see that all of these grids intersect our characters. Let's turn off the UV display, and we can see that in fact our grids do intersect, and we can use these now as cutter planes to create the slices that we need. And in fact, we can probably start doing this with the next lesson, and it's worth saving this geometry as it is for now. We can do a file cache. We'll place this in the job folder, and let's do here, we'll do sliced planes, and we want to save this from 1200, and we'll save this up until the last frame. So let's save to this and give this a second. All right, and now we can, let's drop down a null here, and this will be our out sliced planes. And with the next lesson, we can start working on our RBDs. And we can start working on our RBD setup now. And in between lessons, I went ahead and labeled all of our setups here. So we have our curves, our lead points, our slice particles, and our slice planes. And just a quick note on our slice planes, we will also need UVs. So I have the UV display turned on, and we can see we don't have any UVs. And we can fix this by just going to the sweep node here and turning on in the UVs and attributes tab over here. We can compute UVs, and now we also have UVs on our planes. We won't need this to texture the grids themselves, but we do need to transfer the UVs to our sliced geometry in order to create the interior faces material when we slice up our geometry. So we just need UVs on our planes. We just have to turn this option on, and now I will go ahead and recache our geometry. So our planes will now have UVs, and let's go ahead. We can go up and we can work on our RBDs. We'll do a new geometry container, and I'll call this one effects RBDs. Let's do something like this, and let's also color this blue. We'll step inside and we'll want to grab our remeshed version first of all. So let's go over here, grab our out remeshed node, and we'll step inside, do a object merge, and let's paste this over here. So we can set up our cutter geometry right away. We will need to reference the planes that we just cached. So let's also go up, and inside our slice PRT, we'll also need to point to this geometry here. So I will grab this, Control C. Let's go back, and I'll duplicate the object merge, and let's paste our planes over here. Now, we can run a Boolean fracture on this as it is, but it's worth optimizing this cutter geometry a little bit. We really only need these planes to exist right outside of our enemy geometry. So from our object merge over here, let's go ahead and we'll do a VDB from polygons. We want to use an SDF and we want to fill interior. And probably we can lower the voxel size a little bit so it's more accurate. But this is what we want to do, and we will use world space units for the narrowband, which means that this will just increase the bounds outside of our geometry of this SDF. So we can increase this to something like 0.2, and we need this information outside of the geometry in order to create a group based on this SDF. So from our object merge, from our grids, if we do a group node from here, we can leave this as primitives, and let's disable base group and keep in bounding regions, and we'll use bounding volume. So now I can point this to our VDB from polygons, our second input here. And this throws an error, probably we can't use primitives, so let's just set this to points. And we can see, we can kind of see a selection here. Let's go ahead and right away we can run a blast node, and we can do let's select this group 1 and let's delete non-selected. So we see what we are left with. Let's template our geometry with E so we can look at this more better. So now what we can do is go inside this group, and I can increase the ISO surface value over here. And this ISO surface is tied to our exterior band. So whatever option we have here should be the same value in our ISO surface. So we can probably extend this even further, and this means that we will have to, let's actually just link these settings. So I'll set this to 0.3, and I will copy parameter and just paste relative references over here. So now as I increase this, we increase the bounds. Maybe we can template this and just preview our geometry instead. And I think something like this will be fine. We can see all of our geometry for our cutting planes has quite a bit of padding in relation to the geometry that we want to cut. So I think this will be good. Let's also turn off the UV display. All right. So from this blast node over here, we will have some stray points that might mess up. We can see this over here. Let's set this back to points. We can see we have all of these stray points that were left over from this blast. So let's also run a clean after this, and let's also do an attribute delete. We want to get rid of all of the attributes except our UVs, which we want to transfer. So here I will select the UV in the vertex attributes and delete non-selected, and let's make sure that the UVs are still there. All right, so it works. And now we can use this in a Boolean fracture. From our remeshed version over here, we can do a Boolean fracture. But before we run this operation, and let's also plug our cutter geometry in the second input, and in fact we can probably also do a null after this attribute delete, and we can rename this one to cutters. And before we run this operation, on our remeshed geo over here, if we go to the geometry, let's maybe go to the geometry spreadsheet from here, we have a name attribute, and this name attribute was transferred over from our convert VDB operation, where we turn our SDF back into a geometry. We were left with this name, and whenever we have this name attribute, this might mess up our Boolean fractures. So it's best to just get rid of any name attributes before you are running this Boolean operation thing. So let's drop down an attribute delete, and here we just want to delete our name attribute. We don't really need our class either, but we really need our path. In fact, here we just need our path and our UVs essentially, but we can keep our class. It won't bother us, but we do need to get rid of this name attribute. So hopefully now if I run this Boolean fracture, we have the result that we are after right away. And if we do an exploded view, let's take a look, and I think from the looks of it, everything works. So this is where all of our slices happen, and everything seems to be looking good. We don't have any weird issues happening. We can see that this is pretty consistent to where our grids are. In fact, if I set this to a low value here and preview my cutters, we can see that indeed everything worked fine. So now it's probably worth saving this geometry as it is. It's probably good to do a file cache. Let's turn off time dependent cache, and this will be our, let's do RBD pieces or something like this. We can set this to our job variable and we can save to disk. So, okay, this will be, let's drop down a null, and this will be our out RBD pieces. And for our actual RBD simulation, we are going to keep things extremely simple. We will just add a velocity attribute for our pieces and just simulate them as they fall down and collide with the ground. So from here, we'll use a RBD solver, so RBD bullet solver. We'll drop this in the first input. Let's also create some proxy geometry. We probably don't really need to do this, but it will make things a little bit faster in our simulation. We also need to start this at 1365, so this is where again the switch happens and where we actually want to start our pieces to fall down. And for our proxy pieces, we can just run a convex decomposition on our main pieces here. So let's run this. Let's wait a second. Okay, so this is the proxy representation. Now we can also run our exploded view and we can kind of inspect our pieces. This is what's actually going to be simulated. Let's plug this back over here. So we also need to turn this into a packed object. So let's run an assemble from here, and we want to create packed primitives, but we don't want to change the name attribute. So let's uncheck this. And hopefully now, if I plug this in the third input here, which is the proxy geometry, let's go to our RBD bullet solver and let's see if we have a ground. We will replace the ground with a height field, but let's first go to the collision tab over here, and the ground type we will set to ground plane, and we'll change this in a second like I mentioned. But let's just see if normally our pieces should just start to fall down. So if I play the simulation, this is what we get. All right, perfect. So we can see that our simulation is working, and like I said, we will just create a velocity vector for our pieces, and we can do this on our proxy pieces from over here. So after this assemble, let's drop down an attribute vop. We'll rename this one to set v. Let's color this orange, and if we step inside, we will just grab the position as it is. So we want this vector to point to the center of our scene. So let's grab the position and we can just normalize this. And if we plug this inside the velocity, we should already have this direction that we need. So if I go back to the simulation now, let's see, it's probably going to go in the opposite direction, but we'll change this in a second. But if we run a simulation, we can see that the pieces are slightly pushed to the outside. I'm not sure how noticeable this is, but this is essentially what we want. So we want to reverse this direction first of all, and we want to scale it up by a certain factor. Let's step back inside, and all we have to do here is a negate after the normalize, and we'll also do a multiply and promote the second input here, and we can rename this one to amp for amplitude. And if we go up, let's set this to a value of 3 and see how this feels. And if we play the simulation, hopefully our pieces, we can see they start to fall and they have this initial velocity. So if we run this for a few more frames, this is the result that we get. And I might want to increase this amplitude further. I might want to set this to a value of 4, just so we have a little bit of extra push in our simulation. So something like this, I believe, will do just fine. We can also preview this with our character now. Well, let's turn off the template for our slice, PRT, and also we can hide our enemies for now, so our original geometry. And if we look at this through our camera especially, let's take a look. All right, and this is going to be perfect. So this is more or less everything we have to do for our simulation. Like I said, we are going to keep things extremely simple. If we go back inside, we can just take it one further step, which is to use the actual ground that we have, the actual ground geometry that we have as a ground collision. So for this, we will need to set this ground type here to height field, and we will need to generate this height field. So we will need to grab our environment geometry. Let's go ahead and we can go up in our geo env. Let's grab this null and let's bring this in our chain over here. We'll do our height field setup over here to the side. So with an object merge, we'll bring in our environment. Let's hide other objects, and let's go ahead and first of all we need to unpack USD. So let's do a USD unpack USD to polygons. We'll connect this here. So now we have our polygons. We can just press S. I am in the primitive selection mode, so I can just double click our ground, press delete, and then we can delete non-selected. So now with our ground geometry, we will use this to project to a height field object. So I'll just drag this chain over to the side. We'll drop down a height field object. And here we can probably make this way smaller, and we really just need the ground to account for the area where our RBDs are. So if we go over back to our RBD simulation and let's just simulate this for a few more frames, we'll do something like this. So if we look at our height field, let's template this with E, look at our height field, we can probably increase this even further. We can do something like this. Again, we just need the area where our pieces will actually collide with this geometry. And we'll probably want to decrease our grid spacing by quite a bit. We can use something like 0.2. And if we do a height field project, we can use our geometry now as the second input. And if we look at the result now, we have almost what we need. We can probably lower the voxel size even more. Let's use 0.1 so it's more accurate. The problem here is that we will need to make sure that our height field is below our entire ground geometry. So back to our height field project, while previewing the result of this node, I'll select the height field and I will want to reduce the initial height here. So I will just push this down to maybe negative 0.2 until we get all of the features from our ground geometry back. So now with this height field, I think we have pretty much everything we need. We can drop down a null, and this will be our out HF ground. And we can just point to this in our RBD setup. So we'll grab this, let's copy the path to this node, and in our RBD bullet solver, we'll point to our height field over here. And we don't need deforming geometry. And for our bounce and friction, we can pretty much leave these as they are. You can experiment with these values if you find that the pieces aren't really behaving as you want. But the default settings here will give us a fairly decent result. We might want to increase the friction, but I'll leave this up to you if you want to decide. To sort of account for some of this bounce and friction, we can just go to the forces here and we can just introduce some drag and also the drag spin. And probably we can increase these settings a little bit, and also our drag spin, let's use 0.01 for both of these. So now if we look at our simulation, we can also preview this. Let's show all objects so we can also see our ground, and let's just simulate a few frames and see what we get. All right, so first of all, our ground collision is working, and that's really the last thing that we need here. The only other things will be to play around with some of the settings, but I can honestly say that this is looking pretty good. All right, and really from here we can actually do a file cache, and this will be our setup. So let's run a file cache. We'll place this in $job, and this will be our RPD_sim. We want to start at 1365 and we'll simulate until the last frame, and we'll save to disk. So here we have it, and we can do a null. This will be our out RBD, and we can straight away plug this geometry into Solaris and it would work, but we will need a little bit of adjusting. So we'll add some more detail to this geometry when we get to the Solaris part, but for now we are pretty much finished. And let's also run a file cache here from let's do from 1360 to the last frame 1450, and let's also see this in real time and check how our pieces move. All right, so this is our simulation, and because of the drag that we just added on the spin and the main velocity as well, we have a pretty good result, I would say. This is definitely good enough in order for us to continue working on the effects. And with the next lesson, we can start working on a secondary particle effect for the slices. So I will see you there. So we have our main RBD simulation, and we can move on to the next layer, which will be something that I like to call after slice particles, meaning that if I go over in Nuke real quick, I can just show you this rendered layer. So it's going to be this layer here as our slice particles, or rather our slice planes in this case, are traveling through our characters. They leave sort of like in their wake, they leave particles around the sliced areas of our object, as we can see over here. There's a few things going on over here. We can see, if we just focus maybe on this particular slice, that when our slice travels through the character, first of all, it leaves this border around our character, but this border also expands and then contracts over time until it's just a simple thin line again. So if we just go over frame by frame, you can see how this extends a little bit, and then slowly over time it will contract until it's just one simple line like this. So this happens per individual slice. We can see that our new slice that happens over here will also expand and then contract back. So what I would like to achieve with this at the end of all of our slices, when the effect sort of starts to settle, I just want a thin line border around the sliced areas. So if I go forward in time, we can see how this effect will end up. And we can also see that it follows the RBD simulation. So we want this effect to linger for a little bit as well after the pieces start to fall. So that's also something that we'll have to take care of. But first, let's go ahead and try to get our effect in the first state, which is just to leave a trail of white points when the slices happen. So let's go back over in Houdini, and we'll start with our remeshed pieces again, or actually we'll need to grab our RBD pieces. So after we do our Boolean fracture here and cache the geometry, we'll need this geometry. And speaking of which, there is one more thing that we forgot to set up here. Let's hide other objects. Before we run our file cache with our Boolean fracture, after this Boolean fracture operation, we really should have run a delete small pieces operation as well. So after this Boolean, we'll do a labs and do delete. Let's type here delete small parts. So we have to run this as well in order to get rid of any super tiny pieces that might add more complexity to the simulation without really any benefits. So I always want to run this operation on any fractured pieces, and if we use the default settings, we can see that this gets rid of quite a lot of geometry with this threshold. So let's just lower this to 0.01 or something like this, and if we bypass this node, we can see that in fact we do get rid of some pieces. We can kind of see some of this over here. Now this is probably still too much. Let's just use 0.005 or something like this, and hopefully this will just help speed things up, and we don't end up with really small pieces that might be made out of just 3 primitives or something like that. So let's run another file cache, and unfortunately we'll have to run another file cache on our simulation as well. Let's make sure that we reset our simulation. So we'll give this a second, let's reset, and we'll run another file cache over the existing one, and we'll give this a second. So after we have our pieces recached, let's see if everything still works. All right, so everything looks good. So from our RBD pieces over here, let's copy this and let's create our effects over here. We'll do an object merge and we'll bring our RBD pieces. And the reason that we want to use this geometry instead of our original remeshed geometry is because we need the name attribute later down the line. This name here that we got from our fracturing operation, we will need to preserve this in order for our sliced effects to also follow the same RBD simulation that we set up. So we'll see how this works in a second, but here essentially we want to scatter points over this entire geometry, and we will just use an attribute transfer as our sliced planes will travel through the geometry. It will just turn all of the points around the slice planes into white. So we'll go from black to white, and we'll add some other attributes as well. So let's just start with a simple scatter for now, disable relax iterations, and we'll need quite a few points here. Let's maybe start with 100,000 and we'll disable max point limit. Let's also set this to pixels. and we have to make sure that this is not a time dependent setup here. And let's go ahead, and we want to set all of these to black. So we'll append a color and let's set this to black. So now inside the solver, we will want to use an attribute transfer from our grid plane. So if we go up, let's go in our slice PRT, and we want to use the same geometry that we have over here with the slice planes. Let's copy this, let's go back up, and inside our FX RBDs, we'll grab our object merge and let's merge these over here. So here we'll give all of these points a white color. Let's maybe just copy the color node, and for this one, we'll set the color to white. And like I said, from our main points here, let's maybe set the display here. We'll set this back to dark gray. We'll plug this inside a solver, and our planes over here will plug inside our second input. And the solver will also, we should start this roughly where our slices start to happen, which will be at around frame 1200. Let's set this start frame here to 1200, and we'll step inside. So we'll want an attribute transfer from our second input. So this is where we have our slice plane geometry. The input one here is essentially ourselves. So let's do an attribute transfer, and we'll use the second input here. And we just want to transfer our CD. Let's disable primitives, and inside the conditions, let's give this a very low value. Let's start with maybe 0.1. So now if I run the simulation, we can see as our grids, let's maybe template this, as our grids start to pass through the geometry, it's going to turn all of the points that's around our planes into white. So let's maybe disable this so we can see that this is the result that we currently have. Now, right away, this transfer distance is way too high. I would like something a lot smaller. So let's go back here and let's maybe try a value of 0.01. So if I run the simulation now, we kind of see something happening here. The problem is that, first of all, we really don't want any points inside our mesh. So if we go up here at our RBD pieces, we want this to be sliced up because we need this name attribute, but we don't want any of the interior pieces to exist. So if I do an exploded view, let's maybe decrease the uniform scale. I really don't want any geometry on the inside here. So from this object merge, let's run a blast and let's select here our inside faces. So if I do the exploded view from here, we can see that this will now get rid of all of these interior faces. So that's one thing that I would like to happen. And if we go back to our solver, let's run this for a second. But now we see that we do have this distance. We can kind of tell that this distance will be all right. But the problem here is that we don't have enough points on our geometry in order to create this effect. We can see that this distance between each point is quite high. So this is why the attribute transfer is not picking up any of our points that we need. Only really a few ones. So maybe I can template the geometry and we can see what's kind of happening here, or maybe the scatter instead. We can see this very large distance between this point and this point. So for example, here we'll get a few of our points turning white, and maybe here as well, but there's going to be this entire gap in between. So we need a way somehow to add more topology or more resolution on our sliced geometry. So we can do this if we run a subdivide, although this will be, because we already have quite a bit of primitives, this will be a fairly expensive operation. So maybe we can increase the depth here to a value of 2. And now if we template our scatter to points, we can see that probably this will be enough resolution. Maybe we can go all the way to 3 just to make sure. So now hopefully we have enough resolution for our effect. If we run this for just a few frames here, now hopefully we can see that we do in fact end up with this entire sliced area here. Probably we need even more just to be safe. So I'll set the depth here to 4 and let's run this one more time. Let's play this. And we can see now that this will be extremely slow, as this will be cached at any second, because this is essentially an animation. So this will slow things down quite a bit, but if we run the simulation one more time, we can see now that pretty much all of the points that we need are being covered. So moving forward, it's worth just caching this simulation as it is, meaning just the geometry of our planes. Probably I would say that 4 might be overkill here. Let's just use a value of 3. This should be fine. And as I play this animation, we can see that let's maybe go to our object merge here. And after we get enough geometry here, we can see we run into quite a large number of primitives. So now if we run the subdivide from over here, this will be even slower. So it's going to get progressively slower as we animate this geometry. We can see that now it's really struggling to subdivide all of this, and we end up with around 7 million points. Now we can optimize things a little bit. We really only need this geometry, like in the Boolean fracture example, we really need this geometry to only exist outside of our enemy geometry. So from this object merge here, let's run the same setup that we had with our VDB from polygons. In fact, we can probably grab all of these nodes here. And we probably don't need the attribute delete, but we might as well keep it. So we'll grab all of these and let's paste them over here. And our object merge also here, this points to our slice plane. So if we just run this setup, we can see that after this blast and after our clean, we end up with something like this. So we'll run our attribute delete as well. And now that I'm seeing this, in our cutter example over here, when we run our Boolean fracture, really this object merge should have been frozen at frame 1365. So over here, I will do a time shift and I will freeze this at 1365. Because this operation really shouldn't be a time dependent setup. So if we run our cutters and our Boolean fracture, we should get rid of this green stopwatch icon over here. All right, and also our delete small parts. So this is really how we should have set up this cutter geometry. So just make sure that you add this time shift over here. The result will be the same because we cached this when we were at 1365. So I don't really need to resave anything, but we can move forward with our other setup. So we have, let's maybe run this one more time. We'll disconnect this. And just to be sure we are on the same page, we have our slice planes as we have set them up in our other container. Then we have our remeshed geometry over here. We are turning this into an SDF with some exterior padding. We are creating a group based on this SDF, and then we are removing all of the points outside. We are running a clean and an attribute delete, and now we can plug this inside our color and we can run the subdivide only on these few primitives here. So if we run the subdivide, we have this result. We can probably change the algorithm here to open subdiv loop, and we can see that now as I move frame by frame, this will be a lot faster to compute and we'll have the same result hopefully in our solver. If I just simulate this for a few frames, I can say that I'm pretty happy with how our border particles look over here as our grids are passing through. So we can run this for a few more frames, but we can see that slowly as our plane geometry starts to accumulate, we are going to have slower and slower feedback here. So it's just worth saving this geometry from here. Let's do a file cache, and this will be we'll place this inside the job variable. So we'll want to run this from 1200 to 1365, which by the time we reach this point, all of our sliced plane geometry will already be fully animated. And this can be our, let's do subdivided planes or something like this. And let's save to disk. This will take a second, so we'll get back here when this is done. All right, so now we have our file cache. We still end up with quite a few primitives, and just loading this into our scene, we can see that we don't really get instant feedback, but this will now allow us to run the rest of our setup a lot easier. So we'll go back to our solver. This is the result that we have, and there's a few things that need to happen over here. First of all, this expanding and contracting of our border regions here can be based on an age attribute that we set on our particles. So again, just like we do all of our other setups, when our particles turn white, we can start increasing an age attribute, and we can go back inside our solver. We can do this with the same attribute wrangle that we always keep using. So here we'll say, let's zoom in on this, we'll do if at cd.x bigger than 0, then at age plus equals 1. So when our points turn white, we are going to start incrementing an age attribute. Let's rename this one to add age as well, and we might as well do this a pale yellow color. So we can go up and we can reset the simulation, and now we have our age attribute as we turn the colors, as we turn the points to white. So we'll do an attribute VOP, and what we can do to get this contraction, we can create a gradient by measuring a distance from each of our black points to our white points. So if we do a blast node from here to just filter out our black points, we can set this expression here to be at CD bigger than 0, and we'll run this over points and delete non-selected. So now we just have our white points. Let's plug this as our second input inside this attribute VOP, and here we can rename this one to, let's just do something like a gradient, and we'll color this orange. So if we step inside, we can open up a point cloud on our white points by using a PC open to retrieve their position, and then we are going to measure the distance to our own position, meaning the black points. And let's maybe set this to point display for now, and maybe just decrease the point size slightly. All right, so if we do a PC open, we can point this to our white particles. We want to grab this from our own position. Search radius, will leave both of these options as they are, and we will use a PC filter to return the average of the white points position. So the channel here by default will be P, and if I run a distance from our own position to the position they find on the white points and plug this as the color, we don't really have exactly what we want from the beginning. But if I do a fit range from here, let's set the destination mean to 1 and the destination max to 0. And now as I decrease the source max over here, we should start to see that we slowly get the gradient that we are after. So we can do something like this, and maybe we can set this back to pixels so we can see this better. And if I move away a little bit and zoom out, we can kind of start to see this gradient. And maybe we can decrease this source max here, and also now we can start playing around with our values here. So by default, the search radius is too small, 0.1. It's really just going to be up at around, if we look at any of where our white points are, we kind of need to expand this beyond a 0.1 value. So let's just increase this to maybe 0.3 or something like this. And for the number of points, we can see that as we start to increase this, we get a smoother result. Now we probably don't really need as many points. Let's keep this at a value of 10, and we can just go back to our distance over here, and we can play around with the setting. We can also introduce a ramp. So if we do a ramp parameter, we can rename this one to ramp underscore distance, and let's paste this in the label as well. And also let's make this a spline ramp. So now if we reset this ramp and we turn this into an exponential ramp, hopefully now we should be able to see this gradient even better. And we can probably promote our source max, although we will link this in a second to our age. So let's not promote this for now, and maybe we can just increase this like so. And we can see this especially from a further away angle that we do in fact have this gradient that we are after. So this is the first step in our setup. We will probably need more points so we can see this better. Let's run this setup over 1 million points. So we'll go to our scatter here and add another 0. And let's go ahead and reset our solver. All right, so now we can actually start to see this gradient that we are after, which is perfect. So essentially now, if we just look at our source max, as I start to increase this value, we just expand our gradient, and as I decrease this value, we just contract this. So we just need to link this source max value to our age. So this whole animation happens when our particles start to age, and it's going to be tied to our age. So we can bring in the age attribute. Let's just do a bind. We'll bring in the age, and let's do a fit range, and each frame we are incrementing the age by 1. So let's say that maybe after or rather over a duration of 70 frames. Let's set the source max here to 70. We want this whole expansion and contraction to happen. We will also need a ramp to control this transition further. So let's plug this inside a ramp, and this will be our ramp underscore age. Paste this here, and this will be a spline ramp. Now this ramp will output values from 0 to 1, but the ranges that we need to use in our source max here, we can see that we need to go from roughly 0.33 or something like this to maybe a value of, if we go all the way here, maybe a value of 0.01 or something like this. So whatever ramp we set over here, we know we want to remap these ranges from 0 to 1 to the values that I specified. So let's set the destination mean here to maybe let's do 0.01, and our destination max to be 0.3. And I will plug this result of the fit in our source max, and we can go up. And the ramp that we need for our age over here, we need to go from 0 to 1 very quickly and then slowly fade this back to 0. So we'll just add a point here roughly in the middle but more towards the beginning, and we'll set this to a B-spline. Let's add another point over here, and we want a smooth, slow tapering out like this. So we can see that this isn't working right away, and actually while we are doing some tests, let's set the scatter amount here back to 100,000 and reset our simulation just so we get a little bit faster feedback while we are setting this up. We can see that it kind of works, meaning that we are fading this result in, but we are not really getting the result that we want. So let's go back inside, and if I were to disconnect this, and again I will just set this myself, we can see that the values here are working. So whatever values we are exporting here are not correct, and this is because we are grabbing the age as it currently is. So if we go up, our age only starts to work when the points turn white. And since we are running this operation mostly on our black points, this age will be 0 for most of these points. So we will need to grab the age of our white points instead. So we will go back inside, and we need to grab the age from our point cloud that we are running on our white points. So over here, after this PC open, we grab the position of the white points, and with another PC filter, let's duplicate this, we can grab the age of these white points as well. So we'll set the channel here to age, we'll set this to be a float channel, and we'll replace this in our setup here. Let's run our fit range after this PC filter. Let's get rid of this bind import here. So we have our age. Let's also maybe rename this one to filter age, and this first one will be filter P. So we grab the age of our white points, and then we are using this fit range. We are running this over 70 frames. We have our ramp over here, and finally we are exporting these two values over here, and we can plug this result now hopefully in our fit range after the distance. So if I plug this inside the source max, we hopefully should have the result that we are after. And now we can see that when the slice happens, we have this expansion, and then slowly over time we are contracting back to roughly the initial position from which they start. So we have something like this, and we'll need to run this over more points, but probably our destination mean over here, we can probably increase this to maybe 0.02 as our final value on which this effect settles. So let's maybe organize things a little bit here. And we can just go over this setup one more time. With this PC open, we are looking at our white points, which we have over here to the right with this blast node. And then we are grabbing the average position of our white points and then the average age. We are generating a distance based on this found position. And we are filtering this distance through a ramp, and the source max from this fit range operation is controlled by the age of our white points over here. So it's spanning over 70 frames, and now we can probably promote some of these parameters as well. If we promote this one, this can be, maybe we can set this to a age max or something like this. So over 70 frames, we have our ramp age over here, and then we have our minimum and maximum values on which our gradient can expand. So we can promote these two as well. We can rename this one to gradient min, and this one we can rename to gradient max. And then all of this is filtered through another ramp, which can further control this gradient. So now let's go back to run this over 1 million points, and let's reset our simulation. All right, and we can simulate a few more frames over here, but this is roughly what I want to happen. So we can clearly see our gradient, we have our expansion and contraction, and we can further control this ramp over here. Maybe we want to make this have even more of an exponential fall off, so we can do something like this. And in our final result from over here, basically we can get rid of all of the points that are black, so we can run another blast node with the same expression at CD greater than 0. We'll run this over points, and if we delete non-selected, we get rid of all of our black points. So this will just help us optimize things a little bit. And the last thing that we need to set up here is have all of these points also follow the pieces as they start to fall. And from this blast node over here, I will just freeze the simulation as it is in order to create this setup. So we'll do a time shift, and I'll just freeze this at our current frame. And again, this is just so I can explain things and see if this setup will work. But in order to make our points follow with our RBD simulation, we could use a point deform and just match it with our RBD geometry. But really an even better option here, because we are working with RBDs, we have access to the transform information for all of the pieces. So if I step inside this RBD bullet solver, I will go ahead and right click and choose allow editing of contents. And if I step inside, over here we see that we have our three outputs basically, which we have over here, and we have our main geometry, which we are exporting. And if we just look above, we have these transform pieces, which is how we usually do RBD simulations. And we can see that our second input over here is going to be the template points. So if we follow this trail up and we go further up until we reach our DOP import, this node over here will contain our points representation of this RBD simulation. So probably let's go to our RBD bullet solver and let's run this over a few frames. So we actually have some information here. If I step back inside, we can see our DOP import. If we turn this to points, this is our points representation. So we can just use these points to move our particles as well. And we can just drop down a null from here. So we can point to this. We can do out RBD PTS or something like this. We can copy this. Let's go up. And if we do an object merge, we can just bring this at our sub level as well. And now with this object merge, we just get our points, and we can probably also cache these as well. Let's just run another file cache here from the same frame range. And this will be our RBD. Let's do PTS and let's save to disk. So now we have this here. And we'll grab this and we'll move this over to our particle setup here. So we want to use the same method with a transform pieces operation, and we'll just use our RBD points as the template points. The problem here is that this won't work right away. We can see we have a messed up result, and this is because we need the same name attribute to exist on our points, the same name that we have on our pieces. So over here, back where we import our RBD pieces and we do our scatter, when we do our scatter, we lose our name attribute. So we no longer have this over here because it exists on the primitive level. So we can go to the output attributes over here and we can select to bring in some primitive attributes as well, which in this case, we need the name attribute. So now we have this on our points. We can see this over here, and we'll just have to run our setup one more time. So if we go to our blast, let's also give this a second to recache our solver as well. So now at frame 1274, where we froze our geometry, if we look at our information, we have our name attribute, and now in our transform pieces, we see that everything will fall along with our RBDs. So if we play this animation, we have this result. So this is exactly what we need. And now we can save this entire simulation out. We'll need to get rid of this time shift. This is just here to troubleshoot our RBD setup with the transform pieces. So we'll get rid of this. We just have our blast, and we can run a file cache from here from 1200 And we'll run this to maybe 1400. So we really just need these points to exist for a few frames after the RBD simulation happens at 1365. So we'll just use here 1400 as our end frame. Now we just have to take into account that in order to use this frame range over here, our sliced plane geometry, this file cache that we have on our high quality, our high resolution planes, this also will stop at 1365, so we need this geometry to exist up until frame 1400. So we can just use a time shift over here and we can clamp to last, and our last frame here should point to 1365, which is the last frame that we cached. So if we run this time shift now, we see that our animation essentially for this slice geometry will last up until the end, up until the last frame of our timeline. So from here we have everything we need. One final thing to optimize our file cache will be to do an attribute delete, and after we simulate everything that we need, we just want to maintain our color, really our gradient. So here I'll set this to CD and delete non-selected, so we can get rid of the name attributes and all of the other attributes that aren't really needed. We just need this color for our material. So currently we are running this over 1 million points. Now for our final simulation, we can probably bump up this number. We can go to our scatter here, and in the options, let's maybe use 3 million instead. We'll set this to 3 over here, and we can run our file cache now. Let's do $job, and this will be our after slice PRT. We'll go from 1200 to 1400, and we can save to disk. So let's take a look at our result. We can play this for a few frames and let's see if everything is working. And I think we have everything we need. If we show all objects, we can probably also template this. Let's turn on our enemies and go back to our effects RBDs and from our camera. Now this won't really be the most accurate representation of how this effect will look in our final render, but we do have in fact everything we need. So from here let's just do a null, and this will be our out after slice PRT. And now essentially with this layer we have everything that was connected with each other in terms of the slice effects, meaning that with the next lesson we can start working on all of the other effects that we can just add on top and that aren't really connected with each other. So I will see you in the next lesson.